Can I start?
Maybe just 3 minutes. So okay. Perhaps somebody will also join us. And
okay.
Usually we start at 10:00.
Okay.
Well, okay, I suppose we could start. Thank you everybody for coming, and the leader of this seminar asked me that I introduce our speaker for the day because Štefko Mitrović mentioned that he has some other obligations today. So it's my pleasure to introduce Dr. Hassan Cheraghpour from University of Kurdistan in southern Dash, Iran. And he obtained his PhD in 2018, also from University of Kurdistan, under supervision of Professor Nader and Ghosseiri. He works in algebra, finite rings, and ring theory. And today he will talk about on the idempotents, nilpotents, unit, and zero-divisors of finite rings. So, Dr. Cheraghpour, the stage is yours.
Thank you so much. Greetings and regards, dear Professor. Thank you for time you have given me, especially thanks to Professor Kuzma for preparing the groundwork of this seminar. I am delighted to be here today to talk about on the idempotents, nilpotents, units, and zero-divisors of finite rings. That is based on the paper was published in 2019 by me and my supervisor, Professor Ghosseiri. In this talk, we find the number of idempotents, nilpotents, and zero-divisors of matrix ring, our finite field. Next, given the order of the Jacobson radical of finite unital ring, we find the number of units, nilpotents, and zero-divisors of R, and give an upper bound for the number of idempotents of R. Next, we find the above-mentioned numbers in some matrix rings and quaternion rings. First, we have say some history about this topic. Study of finite rings, and in particular these elements have a great story in algebra. For example, Hall and Feynman-Röstein, Gershenhaber, Lucy Crabb, and so on worked in this topic. For idempotent elements too, for example, Stager and McHale work in idempotent elements. First, we have some definition and theorem that will be needed in next. Assume that R is a ring and element E in R is called an idempotent if square of E is equal to E, and an element A in R is nilpotent if there exists a positive integer such that R to the n is equal to 0. A non-zero element A in R is called right zero-divisor if there exists a non-zero element B in R such that BA is 0. We can replace right by left in this definition. An element A is called zero-divisor if A is both left and zero-divisor. An element A in R is called right invertible if there exists an element B in R such that AB is equal to 1. Also, we can replace right by left in this definition. An element A is called invertible or unit if A is both right and left invertible. Let R be a ring with identity. The intersection of all left maximal ideals of R is called Jacobson radical of R and denoted by rad of R. In the definition of rad of R, we use the maximal left ideals of R. So radar should be called the left Jacobson radical of R. And we can similarly define the right Jacobson radical of R by intersecting all maximal right ideal. It turns out that the left and right Jacobson radical coincide, so the distinction is after all unnecessary. Note that rad of R is an ideal of R. Let R be a ring and M be a left A module. M is called semi-simple if any submodule of M is direct summand of M. And a ring R is called left semi-simple if it is semi-simple as left R module. A ring R is called J semi-simple if rad of R is equal to 0. We need this definition in next. Now we have a structure theorem in non-commutative ring theory, Wedderburn-Artin theorem. Let R be left semi-simple ring. Said we have this isomorphism, ring isomorphism. For suitable division rings, D1 to DR and positive integers N1 to NR. The number R is uniquely determined as the pairs N1, D1 to NRT, DR up to permutation. There are exactly R mutually non-isomorphic left simple module of our R. We have a theorem that is this theorem. A left semi-simple ring R is always right semi-simple, and conversely, from now on, we may therefore speak of semi-simple ring without the adjective left or right. A ring R is called left Artinian if any decreasing chain of left ideals of R is eventually constant. Now we have this theorem about semi-simple ring, J semi-simple ring, and left Artinian ring. A ring R is semi-simple ring is semi-simple if and only if R is J semi-simple and left Artinian. A ring R is Dedekind finite if for any A and B in R, if AB is 0, then BI is 0. We have another theorem about relation between left Artinian and Dedekind finite. That is, any left Artinian ring R is Dedekind finite. And another theorem, let R be a left Artinian ring, and the non-zero element A in R is left zero-divisor if and only if I is not right invertible. Also, we can replace the right by left in this theorem. But since we consider only the finite rings, since they are Dedekind finite, any finite ring is Dedekind finite, and left and right invertibility of elements coincides. Moreover, they are left Artinian and left and right zero-divisors coincide. So from theorem, the theorems above, we have this corollary. Let R be a finite ring, since the non-zero element A in R is a zero-divisor if and only if I is not invertible. Now we have another important theorem in ring theory, Wedderburn's little theorem. If D is a finite division ring, then D is a field. Our goal is to find the number of idempotents, nilpotents, zero-divisors, and units of finite rings given by order of radical Jacobson of R. We can find these elements, but we cannot use this radical Jacobson for finding the number of idempotent. So we find a new upper bound for the number of idempotents, which is general smaller than the upper bound found previously. Next, we computed the above mentioned numbers in finite matrix rings and quaternion rings. Now, let F be a field and n is a positive n be a positive integer, and let R be the ring of all n by n matrices over F. Recall that if the matrices A and B are similar, if there exists an invertible matrix P in R such that P is P A P inverse. Note that similarity is an equivalence relation on R. In fact, we use this recall in proving of this theorem, proving of next theorem. Now we recall the following well-known fact in linear algebra, which will be needed in the sequel. Number one, let R be this matrix ring, B as above, and every idempotent element of R is similar to a diagonal matrix whose entries are either 0 or 1. And another one, similar matrices have the same trace. By this theorem, we have this corollary. Let A and B, diagonal idempotent matrices in R, and A and B are similar if and only if they have the same number of ones on their diagonals. It means trace of A is equal to trace of B. Let F be a finite field of order Q and be a positive integer, and let R be the matrix ring over F. Let UR, IR, NR, and ZR denote the units, idempotents, nilpotents, and zero-divisors of R. Respectively, denote their orders by U, I, N, and Z. So we have this theorem. Let RU, I, N, and Z be as above, and we have this computation about unit of R, idempotent of R, nilpotent of R, and zero-divisors of R. Now let R be a finite range that with the rad of R with J that is rad of R, and let the order of J is be K. Since the quotient ring R bar is a J semi-simple left Artinian ring, by the Wedderburn-Artin theorem and Wedderburn's little theorem, we have this isomorphism. R bar is isomorphic to direct the product of some matrix ring, finite matrix ring, where Ni are positive integers and Fi's are finite field. Let order of Fi be Qi. Put U and I the number of this set. Since for every pair of rings S of t we have these three equalities, now we have this next theorem. Let R and Rj and R bar be as above. R was this are a finite range, any finite range. Let R, J, and R bar any finite range, but we know the order of radical Jacobson of R. Then we have this computation, unit of R bar and unit of R, unit of idempotent of I bar, nilpotent of I bar, and R, zero-divisor of R bar and zero-divisor of R. In fact, order of this. But we don't speak about idempotent and number of idempotent of R bar. We know we find an upper bound for this number. In McHale, in reference 5, find an upper bound for this number. He showed that this is a upper bound for idempotent for the number of idempotent of R. Our goal is to find a smaller upper bound for the number of idempotent of R. Let F be a finite field with order Q and M be a positive integer, and let R be the matrix ring over F. Then we have this upper bound for the number of idempotent of R. From a theorem above, we have this theorem that reproves McHale's results in a special case. Let P be a prime and R be a finite range such that order of R is some power of P. Then this is upper bound for the number of idempotent of R. That is equal to upper bound that McHale found. By 5 McHale papers, in the finite ring R, the decomposition of additive group as the direct sum of abelian P groups induces the composition of the ring R as direct sum of ring of prime power orders. Note that this decomposition of R is uniquely determined up to isomorphism. Thus, R is equal to direct sum of R1 to Rn, where order of Ri is power of Pi, and Pi's are the distinct prime divisor of order of R. Since we have this equality for the number of idempotent of R, we have this following this theorem. If R is a finite range and Pi are the distinct prime dividing order of R, then we have this product, this upper bound for the number of idempotent of R. Note that this upper bound is smaller than the upper bound McHale found for the idempotent of R. This theorem has an immediate consequence. If R is a finite range and P is the smallest prime dividing order of R, then we have this upper bound for the number of idempotent of R, wherein is the number of distinct primes dividing order of R. This upper bound is also smaller than upper bound McHale found in reference 5. unless for p 2, p is 2 or n is 1. Okay, so far we find the number of nilpotents, zero-divisors, and units of finite ring of R when we know the order of Jacobson radical of R, and we find an upper bound for the idempotent of R. Our next goal is to compute the number of these elements of the matrix ring, this matrix ring, where n is a positive integer and m is at least 2. First, we obtain this number in this matrix rings over z sub p to the t, where p is a prime and t is a positive integer. Let's RBD matrix above matrix, where p is a prime and t is a positive, t be a positive integer, and let UR unit of R, idempotent of R, nilpotent of R, and zero-divisor of R, and denote these orders by U, I, N, and Z respectively. Then we have this computation about unit of R, idempotent of R, nilpotent of R, and zero-divisors of R. In this case, we can find the idempotent of R, and we don't introduce any upper bound. We exactly find the number of idempotent by this relation. Now let M be this product, and PI's are distinct prime, and TI's are positive integers. Recalling that we have the ring isomorphism. When M is this product, we have this ring isomorphism. And the fact that for every pair of rings, S and T, we have these three inequality. Unit of S product T is equal to the unit of S product unit of T, is hold also for idempotent and nilpotent of for S and T, but it's not hold for idempotent for S and T. So with theorem above, we have the following corollary. Let M be as above this product, and R be matrix ring over Z sub M. And we put unit of the number of unit of matrix ring over Z sub pi to the ti by ui and uri by for this set, so the order of this set, I sub I for order of this set, and n sub I for order of this set. We have the following we have the following computation. That is u unit of number of unit of R, that is R, this matrix ring, number of idempotent of R, number of nilpotents of R, and number of zero-divisors of R. So far, we have found the number of units, idempotents, nilpotents, and zero-divisors for this matrix ring over matrix rings over Z sub M. Our next goal is to find this above mentioned in the matrix in the quaternion rings, but in some cases they are similar, they have similar structures. Now we have a new definition. Let S be a ring with identity set H of S by this set that is equal this direct sum, where square of 2, square of j, square of I, square of j, square of k, and ijk all of equal to -1, and ij is equal to -j1. with the component-wise addition and multiplication subject to the given relation, and the convention that ijk commute with S element-wise, HS is a range, and called the quaternion ring over S. Note that since ij is not equal to ji, this ring is non-commutative, but in some cases, for example, if we replace Z2 by S, since 1 and 1 minus 1 is equal in Z2, that this matrix, these rings are commutative, but in general case is not commutative ring. This ring is a generalization of Hamilton's division rings of real quaternions. Hamilton's division rings, that is, we replaced R by S. If we replaced R by S, if these rings will be Hamilton's division ring. But in general case, quaternion rings over S is not division rings. Division rings, what is division ring? Division rings is a is like a field, but may not be commutative in for product. The commutative is may not be commutative. For some information about quaternion ring and some mapping on these rings, one can refer to reference 6. Now, our goal is to find the number of idempotents, nilpotents, units, and zero-divisors of quaternion rings over Zm, where M at least 2. It is straightforward to prove for any S1 and S2 quaternion rings of S1 product S2 is isomorphic to quaternion ring over S1 product quaternion rings over S2. This is ring isomorphism. Now we have the famous theorem in algebra that says if F is a finite field, then there exists alpha and beta in F such that this equation holds. From this theorem, we have this theorem that is interesting in itself. Let F be a field, not necessarily finite, maybe infinite, whose characteristic is an odd prime number, number P, and let S be integer, let S be an algebra over F, then we have this algebra isomorphism. We remark that if a field in the theorem above is not finite, gives yet some useful information about the units, nilpotents, idempotents, and zero-divisor of S. But our work in this case is about finite ring. Then we turn back to finite case. Let P be an odd prime number, noting that for T at least 2, Z sub power of P is not filled. In order to show that this ring isomorphism, we need the following lemma, which is interesting in itself. This is similar to this theorem, but for this range, Z sub power of P. Let P an odd prime number and let T is a positive integer, and there exists alpha and beta in the ring, in this ring, such that this equation holds. Using the lemma above, one can easily verify that if P is an odd prime number and T at least 2, then we have this ring isomorphism. we have this ring isomorphism. From this theorem, we have an immediate corollary. This corollary says if n is odd integer for any integers, but odd integers, for any odd integers, we have this ring isomorphism. Since we found the number of matrix rings over the ring Z sub n, and we have this isomorphism, we can find the number of idempotents, nilpotents, zero-divisors, and all of them in quaternion rings over Z sub n. But if n is even integer, this equality, this isomorphism is not holds. The following example shows, however, the oddness of n in the corollary above cannot be suppressed. Example, let n be even integer, recalling that every homomorphic image of an m by m matrix range is again an m by m matrix range. We conclude that every homomorphic image of matrix range is a matrix range. Then also we have, if this is matrix range, so this is homomorphic image of this matrix ring. This is homomorphic image of matrix ring, and so this is a matrix rings. But we know this is not a matrix rings because matrix rings are non-commutative ring, but this ring quaternion over Z2 is a commutative ring. Then this is not commutative, and so this is not commutative. Then the oddness of n in the corollary above cannot be suppressed. But we can find the number of idempotents, nilpotents, units, and zero-divisor of for even integer n in next. For the case n is odd, we can find so far we find the number of idempotents, nilpotents, units, and zero-divisor of quaternion ring quarter over Zn. Hence, to find this number in the general case, we should them in this matrix, these quaternion rings over Z power of 2, where t is positive integer. To do so, we have a new characteristic equation. It is similar to characteristic equation of matrix ring. Let S be a commutative ring, and let R be quaternion ring over S. For any A in R, we have the following characteristic equation. This characteristic equation, where this notation is equal to A times A bar equal to sum of square of A, B, C, and D, where A bar is equal to A minus BI minus CJ and minus DK. That is called conjugate of A in R. This characteristic equation is useful for next theorem and useful and interesting in itself too. No, we already described some properties of the quaternion rings. The quaternion rings of Z power of t. Let R be this ring, quaternion ring over power of Z power of 2. Then R has the unique maximal ideal rad of R. Moreover, we have we compute unit of R, nilpotent of R, idempotent of R, zero-divisor of R, and their orders. So far, that is we can find the number of, since we can find the number of idempotents, nilpotents, zero-divisor units of this quaternion rings, and theorem above and this corollary, we can find the number of idempotents, nilpotents, units, and zero-divisor of all quaternion rings over Z sub n for any n at least 2. So our work in this topic was this, that is, we can find this number in finite rings with given order of radical Jacobson of R, and computed them in matrix ring, and then compute them in quaternion rings. These are our references: Brouwer, Crab, Dixon, Fine, Rothstein, Gershenhaber, Kahramani, Hall. Our references: Hoffman, Lamb. This book, these references is the important main refrain in non-commutative range, and so on. And many thanks for your attention.